I don't forget, but it could be that I do forget. And then let's do the share screen. Okay. Yeah. Okay. So last time I gave you kind of a very broad introduction and motivation about particle physics. I told you, so quick recap, very quick on last time. So I said that the particle physics deals with the basic laws of nature in the most fundamental form. So what are the laws of nature? In the most basic form, which is a very big title. And under that, there was what are the fundamental ingredients of matter? What are the basic forces? What are the underlying principles that lie behind them? And of course, what the answers to these questions can tell us about the universe. We describe what is a particle. So it's essentially this is a point-like particle, which is really, we consider it as being a quantum state, which is characterized by quantum number. And then we discuss a little bit on how do we study these particles. We said that there are three ways of studying them. This is via experiments that include scattering, decay, and looking at bound states. These are the tools that we have. We spoke a little bit about where do we get the elementary particles that we're interested in studying. And we said this comes from cosmic rays, from nuclear reactors and particle accelerators. And okay, and then I just mentioned a few things about the detection and the difference between mechanics, classical mechanics, quantum mechanics, relativistic mechanics, and a certain model, a specific model about a particle. This will be, it's not just a semantic, you'll see down the line. Then I made a small table talking of where we are. So I said that as things go from big to small, so smallness goes in this direction, and from slow to fast, so fast goes in this direction. Then we switch from classical mechanics. When things get small, then of course it's quantum mechanics. And when things get fast, it's relativistic mechanics. And when things are both small and fast, it's quantum field theory. And I mentioned to you that in order to do everything properly, we do have to know first quantum field theory, so that you know what is the general framework. Since we don't do it, and I do not assume that you know it, and I want to emphasize that. So if you have not studied it, that's okay. I will teach you some parts of it will be taught. Actually, some part we'll start teaching today. So it actually will be helpful to you, I believe, when it comes to what those of you who will study quantum field theory in the future. I told you that the heart of the QFT, there is the Lagrangian, and that it contains all the terms that are invariant under all symmetry operators. So in that sense, the symmetry properties of the Lagrangian define the model. Okay, then I told you that the standard model of particle physics is known as standard model. which is a model which is based on the quantum field theory formalism and is in excellent agreement with all the experiments that were carried. But I did say that there are clear evidence that it is incomplete. And in fact, some of you asked me, one of you asked me, what are the evidence? I didn't answer. Actually, I could have answered, and I just didn't think of that at the moment, because there are various levels of answering. So why it is incomplete? So first, from a theoretical perspective, it is not consistent with general relativity. Quantum field theory is based on construction of quantum mechanics and special relativity, but a theory that merged quantum mechanics and general relativity, to the best of my knowledge, was never completed. I mean, I think string theory tries to do it, but I'm not a string theorist, so I cannot comment on that too much. And we do know that either one of them or both of them fail at a certain locations, especially when it comes to singularities inside black holes or the beginning of the universe. More about that for those of you who will take the course in general relativity. But either one, something there is inconsistent, and one of these theories at least, or both of them, is not working. So the problems, I'm just mentioning it briefly because I will speak about the, not this week, but the lectures next week. So some problems, I said, inconsistency with GR. And other problems, it's not a real problem. It's at the boundary between particle physics and cosmology. So we know that today in cosmology, the matter that we do understand its behavior is only 5% of the content of the universe. Another 26% is what we know as dark matter, what is known as dark matter. So this is a matter that attracts gravitationally, but we do not see its interaction any other way. So it does not emit light. That's why I call it dark. We don't know what it is. And another, independently, another 69% of the energy content of the universe is what's called as dark energy. This is something which is even stranger than dark matter. It's not a matter at all. It's some sort of energy that causes the universe not only to expand, but to accelerate. And this is something which we can measure, but nobody has any clue what it is. Dark matter, there are some ideas, at least dark energy, to the best of my knowledge, there are no good ideas so far. So dark matter and dark energy, these comes in the realm of, again, astrophysics and cosmology, but they are not anywhere within the standard model. Other issues are the neutrino masses. Neutrinos were believed for a long time to have zero mass, but we know today that they do have a small mass. It's not easily explained. And another maybe also important issue about that is the asymmetry between matter and antimatter, because the theory itself is symmetric. It would tell us that half of the universe should be made of matter and the other half should be made of antimatter. But of course, this is not what we're seeing. Nearly 100% of the universe that we know of is made out of matter, not of antimatter. So there must be something that breaks the symmetry. And this is something which we don't fully understand. And there are some issues related to this, it's called CP violation, a strong CP violation. There needs to be something that breaks the symmetry, and we never saw anything like that. So it's kind of in the big questions that, that it fails, or it doesn't really fail in that sense, but there is some hints that there is something which is missing there. Other things, again, it's not exactly problems, but the standard model has 19 free parameters, which is not a very nice number. People would be much happier if there was a model which is, less degrees of freedom. And also there is some more technical aspect, which is that we'll discuss the Higgs, the spontaneous symmetry breaking of the Higgs field is the mechanism by which particles gain their mass. And it requires fine tuning of it works. We know it works. We discovered the Higgs. Higgs himself got the Nobel Prize for that. But it requires fine tuning of the Higgs mass. And again, fine tuning is not something that physicists like. So these are some of the problems, right? Fine tuning. And then we spoke about matter, antimatter, asymmetry. Again, all these phenomena are something that people hope that they may be solved when we go to higher energies, close to what's known as the Planck scale, in what you might have heard of as the GUT, Grand Unified Theory. I might say a few words about that towards the end of the semester. Right now, I still want to focus on explaining the basics of the standard model.
Is there a reason to think that the matter-antimatter asymmetry is anything more than just symmetry breaking? It had to be one of them?
Well, it is some sort of a symmetry breaking, but we never saw it. It's not part of the model. You would expect to see it, and that the energies that people have seen have been measured so far, it was not seen. So maybe it appears at higher energies. I mean, there is something happened there, right? There's something that caused the universe. I mean, either that the model is incorrect because the model tells you that there should be, 50-50 matter and antimatter, or something else. I don't know. Well, nobody knows to the best of my knowledge, but some people may think that they know. We spoke about natural units. So h bar equal to 1. And that means that everything gets units of energy, and the energy we measure in giga electron volt, GeV. So the units of length is GeV minus 1, and this is equal to the unit of time. No more seconds and meters, or centimeters or microns. Units of mass is equal to the unit of momentum, equal to the unit of energy. So it's measured in GeV. So we said that the particle has a mass, I don't know, the W boson has a mass of 80 MeV, 80 GeV, sorry. That's, you need to do the conversion. Okay, this is as far as we went to last time. It's really the introduction part. Yeah, questions?
Can you give rough value of inverse GeV in terms of meters? So if you say length can be measured in inverse GeV.
I think this will be part of your homework exercise.
Okay.
Just the way we got to that was to put h bar equal to 1 and c equal to 1. So you just have to put the correct values for h bar and the c to get it.
All right, thanks.
Okay, so I told you that quantum field. So okay, any more questions? This is kind of classical for homework. Come on, guys. More questions? I do ask those of you who can to open your cameras. I don't, I won't hold it against you. It's just much easier for me to follow your faces. I don't look at the background of where you are. I don't care about it. But it's easier for me to watch your faces rather than to watch black squares. Any further questions? Okay, so today I'm going to do a special. The lectures today, and I think also the lecture on Tuesday, will be devoted to special relativity. I told you that today I'm going to take the tutorial slot for that because I need to first finish this part before we can do a tutorial. So we'll do that. Okay. The reason why we're doing that, so I said that quantum field theory is merging, of special relativity and quantum mechanics. I'm not going to teach you quantum field theory, but I am going to give you, since we're going to use part of it, then we will be teaching some parts of it, so that at least you'll be familiar with some of the formalism, and definitely the notation and the way things are written, because we will need to make use of those during the course, so that you get familiar with things. And on the way that you learn special relativity, which I believe you already have learned that, but possibly in a somewhat modern language of 4 vectors. This I'm not sure if you did or not. Anyway, those of you who will decide to take the course in general relativity, we will do that in a more thorough and more in-depth way there. But right now, it will give you the necessary background that you need for continued discussion and more technicalities. So today's lecture is going to be about special relativity. By the way, is there anyone around this, this Zoom conference that did not take a course in special relativity for first year or so, second year of studies? Is there anybody for any reason that is not familiar with special relativity? No, okay, I would expect that. So, but I'm pretty sure. What about the notation of 4 vectors? Which one of you is not familiar with that? Which one of you is familiar with that? Is there anybody who did not raise their hands? I think that I saw that there are a few guys who never raised their hands. Okay, I'll go over briefly, and if you feel that you need me to go slower or faster, then do let me know. Right, so I will focus on a few subtle points there. So special relativity, as you know, dates back to when? You will learn that.
1905?
Yeah. No.
1895?
Oh.
Well, technically Maxwell, right? The magnetism already entails all of special relativity.
No.
Maxwell's laws?
No, Lawrence's transformation.
No. 1881 or 7? 7, sorry. Michelson and Morley. Right, behind every successful theory, there is always an experiment. Right, there is always. Why is that such an important experiment?
Because it failed.
Well, what did Michael? Well, no, it did not fail.
It
Well,
failed. It didn't match the expectations. Sorry, let me be.
Not match the expectations. Why? What was the expectation?
To find the ether.
Find the ether. Why did they think there is an ether?
Because they thought that the electromagnetic radiation has to move through something.
Right, right. So if we go backward, right, 1800, right, 18 exactly, 1800, it was Thomas Young who proved that light is a wave, right? And waves go through matter, through medium. So it was obvious that if light is a wave, so if you ask a 19th century physicist, they will tell you, oh, of course, light is a wave. We have Thomas Young's experiment, that double slit experiment. So it is a wave, and we know that waves go through matter, right? And if waves go through matter, then through medium, right? So there must be a medium in which these waves go through, and they call this medium an ether, right? So in the late 19th century, the technology was good enough to detect the motion of light through the ether. If you go even before that, right, in the middle of the 19th century, then Piaget and what's his name? Foucault, the guy with the pendulum. They managed to prove that the speed of light is finite. So there was a measurement of the speed of light by the 19th century. Okay, mid-19th century. So Michelson and Morley did really look for a way of...
You might want to mention there was actually a measurement of the speed of light already in the 17th century.
Yeah, but this was not accurate enough. The one you're right, the Romer experiment, but the mid-19th century was accurate enough. within a few percent. Yeah, and of course they found that there is no ether. So what? Big deal. Well, what's the big deal?
So light goes without without anything to go through.
So what? What's the problem?
That's very counterintuitive at least. A wave going without medium.
A lot of counterintuitive things in physics, but
yeah, but Michelson thought he went through all of them.
Yeah, well, no, there is something which is much more fundamental than that. What's the problem? There is a very deep problem.
I think it implies that the speed of light is independent of the emitter.
What? I could not hear you. There was a noise.
I think it implies that the speed of light is independent of the emitter.
That's true. That's right. And the observer. The emitter is the sun and the observer is us. Yeah, so. Sorry, the emitter is not, excuse me, you're right. The emitter was moving. Yeah, so.
So that's different from anything we know, right?
So yeah, it's independent on the velocity of the emitter. So what? What does it mean?
It's independent of a frame of reference.
Right. So what does it mean?
That light goes in a constant velocity, no matter what you try to do to escape it.
Right. Yeah, that we all agree. But what is the problem with that?
That it shouldn't.
The universe doesn't have a frame of reference.
So what? What basic concepts in classical physics does it fail? Does it not fail? Does it?
Galilean transformation.
Galilean transformation. Very good. So what? So what?
So there is no absolute I.
Yeah. Okay. So what? So Galilean transformation fails. So what?
Then there needs to be something else.
Yeah, but why would I care if Galileo? So Galileo was wrong. So what? Why is that a problem for us?
Because all of mechanics is based on this principle.
Thank you very much. Because if there is no Galileo, there is no Newton. Because the entire Newtonian mechanics is based on Galilean transformation. If you can move to the center of mass, there is no conservation of momentum. There is no conservation of energy. There is no nothing. Then it fails Newton. Now, Newton wrote his Principia, right, in 1687, exactly 200 years before that. And for 200 years, all the experiments that were ever done were in perfect agreement with Newton's laws. From motion of planets to everything, you know, canons and then the motion of objects on Earth, everything was in perfect agreement to Newton's theory. This was the first time that somebody conducted an experiment that showed that Newton was wrong. That's why it is so important. Okay, so the speed of light is constant. And then, of course, 1905, the year of the miracles. 4 papers by Einstein, each of them deserved the Nobel Prize. One of them got it. It was not this one. Okay. It was mathematically beautiful. Everything, what it did was just to replace the Galilean transformation with the Lorentz transformation. It was a mathematical transformation. Henrik Lorentz worked around that time, the late 19th century. Transformation was known. When you replaced it, everything fell in just perfectly. It's a beautiful, beautiful piece. Okay, so we have 2 observers, right? So observer O and another observer, which we call, let's call it the red one, right? O prime. And O prime is moving with respect to O at some speed, at some speed, at some direction, right? Let's say at constant velocity. So observer O would put the coordinates as x, y, z, and time, and observer O prime would write the same coordinates as x prime, y prime, z prime, and t prime. Now I should be a bit more careful, right? Both of them are asked to describe something. So let's say that they're asking to describe this ball. Now in special relativity, which is extremely confusing, the way not to get confused is to speak of events. An event is something that has a specific, occurs at a specific time in a specific place. Somebody scored a goal. This happens at a specific time at a specific place. Two people kissed. That happened. This is an event. So we always think of an event. Every event is described by 4 parameters: the time that it happened and the place that it happened. Okay, the point is that two observers, one is moving with respect to the other, will not necessarily agree on those. Now it shouldn't surprise you, right? We're used to Galilean transformation. So if I'm moving with respect to you, and I'm carrying with me something, then you'd say that the position of this something in your frame is not the same as in my frame. The thing that is different is of course the time, right? In Galilean transformation, we all agree on the time, right? So now let's say that this is a lamp, right? So we have some source of a light, which, without loss of generality, it occurs at t equal t prime equal to 0. So t equal t prime equal to 0, there is a light crest that is emitted, right? So after some time t, so this is an event. A light was emitted. A second event, the crest of the light reached some point, right? So at time t, right, if I ask the observer O to tell me where is the crest of the light, right? It's a spherical wave, so it will say this occurred at x squared, at location x squared plus y squared plus z squared, which is equal to c squared t squared, because the light travels at the speed of light, right? Now I'm asking the same question, observer O prime, which is moving, right? And she will tell me that, of course, the same thing. Since the speed of light is the same, then x prime squared plus y prime squared plus z prime squared is equal to c squared t prime squared, of course, in her, according to her clock. Right? She might be skating relative to the first observer. Right? Who's right and who's wrong?
They're both right.
Both right. Nobody's wrong. Now, again, we assume without loss of generality that the observer O prime is moving with respect to observer O in the x direction. So this is the x direction, right? So in that case, we have that x prime is different than x, but of course y prime is equal to y, z prime is equal to z. So from these two equations, we immediately get that t prime must be different than t. They cannot be the same. Which kind of makes sense because, if both agree on the speed of light, and they disagree on the location, then they cannot agree on the time, because the velocity is the difference in location divided by the difference in time. Right? So that means that the time separation, I told you that I'm speaking about separation because there is two events here, right? Event number 1 is that the photon was emitted, and event number 2 was that the photon reached a certain location. So there is separation between these two events. That's important to not forget. So the time separation is not the same in both frames. right? Now we said in physical language, we said that the time separation is not an invariant quantity. Right? Well, you know all that, right? You know special relativity. So, but we can define a quantity which is invariant. So that is that it conserved when we move from one frame to the other. So that those observers, O and O prime, agree on that quantity. What will that be?
The speed of light.
Well, except the speed of light. The speed of light, by definition, right? We assume it's the same.
The invariant interval.
Yeah, it's called the interval. That's very good. So we call it an interval. It's called an invariant interval or interval. So we define what's called the interval. Right, between two events. Remember, interval is between events. So I'm defining the interval with the interval squared, which is denoted by delta S squared. This is a definition of, right? It's a C delta T squared minus delta R squared, or C squared delta T squared minus delta X squared plus delta Y squared plus delta Z squared. Right, so delta Z is Z2 minus Z1. Now, if you're familiar with the special relativity, you might, if you've seen, have you seen that before, by the way? Because in the first year, the way normally people teach it in first year, they don't show that. Have you seen that before?
They don't show what exactly?
This formalism. But maybe they have. Have you seen that before?
I saw it.
Good.
Perhaps with the opposite sign, but that's
yes, very good. Very good that you noticed that. Very good. This is not a mistake.
Yeah,
I'll go back to that later. I'll go back to that down the line.
all right.
In astrophysics, and relativity is part of astrophysics, there is an opposite sign there. And in particle physics, the sign is different. I'll get back to that. Now I'm following, since this is a course in particle physics, I'm following the notation in particle physics. When you read the particle physics textbook, that is the sign that you find there. It's exactly the opposite to the sign that you find in special relativity or general relativity courses. Okay. Apart from confusing me, I try to think a lot of why is this convention like that, and I found two reasons. So one, well, except for myself, three reasons. One is to confuse me that I have to prepare two courses and make sure that I'm not mistaken by the sign. The second is, of course, to confuse the poor students that take both classes. And the third is to make it very difficult for people in the particle physics community to communicate with people in the astrophysics community. I don't see any other reason.
Isn't there something with geography?
What?
Isn't there something with geography? West Coast, East Coast?
Not that I'm aware of. Anyway, right, so the interval is conserved. Now there is a close analogy. The close analogy is, if we look at the Euclidean space, this is just an analogy. If I look at the 2D Euclidean space, right? And let's say, I'm the observer. So I have X, Y, and I have the concept of, I have 2 points, point 1 and point 2, right? So there is this X1, X2, Y1, X2, and Y2. Right now, let's say that there is a different observer whose coordinate system are rotated. x prime and y prime. Right? So of course the location of each of the points in the new frame, right, is x1 prime and x2 prime, and then y1 prime and y2 prime. Of course, these are not the same, right? You know how to do the transformation, just rotation. But what is conserved?
Distance.
The distance. This distance, right? x2 minus x1 squared plus y2 minus y1 squared is the same as x2 prime minus x1 prime squared plus y2 prime minus y1 prime squared. These are conserved, of course. So it's a distance, right? It's the analogy. So this interval is the analogy of a distance. Maybe easier to visualize. Okay, well, that's the end of the analogy. Okay, now that we get a little bit familiar with that, or maybe I'm just wasting your time because you're already familiar with that, let's speak about Lorentz transformation. But before that, let's speak about notation, right? So the interval that we just introduced connects points in space and time. So it actually merges the space into one entity, which is one space-time. How do we call this space?
Minkowski.
Minkowski, right? This is Minkowski space. That's the space we're going to work on. Now in this space, as I said, we're defining events. Event is defined by its space and temporal coordinate. Right, so T, X, Y, Z. So you need 4 numbers to describe each event. The same way as we need 3 numbers to describe the location of each event in Euclidean space. All right. Now, it is much more convenient that rather than working with X, Y, Z, and T, we're just going to use Greek superscripts with these indices that run from 0, 1, 2, 3. Right. So any event is defined on what we call a 4-vector coordinate of coordinates. Any event is defined by a 4-vector of coordinates, which we denote by X with mu superscript. Now pay attention to the notations. Don't write mu as a subscript. This is not the same as this. Now, in general relativity, we go very deep into what exactly are the differences. Here, we're not going to go very deeply into that because we don't need that. But just make sure that you don't start mixing locations of subscript and superscript. The indices are very important, the location. So the definition is very simple, right? It's x0 is just ct, x1 is just x, x2 is just y, and x3 is just z. This is common notation. You find it everywhere. Is there anybody who's not familiar with this notation? Or it was the first time he sees that? Don't be shy. Who already saw this before? No, it doesn't work like that. There are people who did not raise their hands, not now and not before. Don't be shy, guys. No, physics is not for shy people. There's nothing bad if it's the first time you're seeing that. Of course, there's nothing bad if it's the fifth time you see that. Okay, when we only use spatial coordinates, then normally we replace the Latin index with the Greek index with a Latin index. So xi would normally mean just x1, x2, and x3. X, Y, and Z. These are just the coordinates. I'm not sure how frequent we're going to use just the spatial part of the coordinates. Again, in the course in general relativity, we do make use of that. In here, I'm not sure how much we're going to use that. We'll see. Now, in addition to that, I'm going to introduce a matrix. It's a 4x4 matrix. It's quite simple, and it has a special name. What's the name of this matrix I'm going to introduce?
Lorentz transformation?
No.
The matrix.
The metric. Very good. Not matrix, but metric. Oops. Known as the metric. And I'm going to write it down with two lower indices. Now, the correct way of writing it is using the Greek word of eta, eta mu nu. However, in particle physics textbooks, since people are not really paying attention to the details, as far as I can tell, then you also write it with a G. So it's a G mu nu. You would find both of those in particle physics textbooks. And here's, I'm used to eta to describe this matrix. So I might just switch. For our purpose, it's the same because we're dealing with simple spaces. They're not curved or anything. So it's eta mu nu or G mu nu. And it's a very, I told you, it's a very simple matrix. It's a 4x4 matrix. Mostly zeros, except from the diagonal. Diagonal has a +1, and then a -1, -1, -1. And then everything else is 0. Now, again, indexes are two lower indices, one after the other. This is not the same as this. Well, actually, it does. In this case, it is, but don't do it. Don't play with indices. Rule number 1, never play with indices. In general, right? It should be in general because in this specific case, it's the inverse matrix, which is the same. Now, another very important thing, important. As I told you, the same metric is defined in astrophysics courses and in general relativity, only with the opposite sign. G or not G? I cannot write G. Just it's against my belief, right? It's eta mu nu astrophysics is -1 times eta mu nu particle physics. Again, the clear reason for that is to confuse the students. I don't see any other good reason. Okay, if you're not confused, now it's the time to get you slightly more confused. Now I can write down the interval. I didn't do it for nothing, right? I do it for a purpose. And the purpose is to write down the interval in a compact way. How can I write it in a compact way using this new notation? It's going to be very simple. So delta S square is the interval. You just sum over mu and nu, which goes from 0 to 3. And then eta mu nu, delta x mu, delta x nu. What is written here is exactly as what is written here. Is exactly the same. Do you see that? Do you see that? Good. So if you see that, then you realize that it's so simple that we don't really need to use this summation. So we're going to use, rather than writing the summation, which is kind of annoying, we're simply going to write it down as eta mu nu, delta x mu, delta x nu. We use what's known as Einstein's summation index, Einstein's summation convention, sorry. So Einstein summation convention. Convention is just a T. And of course, Einstein did it to confuse the poor students, which states that every time we're seeing an index that appears twice, once as an upper index and once as a lower index, we simply sum over it. Okay, the index that appears twice, we simply sum over it. If it gets you confused, then simply add up the summation. Just see where you see an index that appears twice. In an equation that is not with an error, the same index cannot appear twice in the same side, unless as an upper and lower index. If the same index appeared twice as an upper index or as a lower index, you wrote something wrong in the equation.
What about the order of the index? Does the lower index have to come before the upper index, or is that?
No, doesn't matter. Look again at this matrix. When I write this, when you see something like that, how many terms do you have here in the summation?
16.
16, right? There are 16 terms here. But
What's
nearly all of
0 in this case?
Yeah, 12 of them are 0, right? Because you just have the g mu nu or eta mu nu, it's mostly zeros. There are only 4 of them that are not 0. Right? So there you do, technically, if you give it to a computer to do, then the computer has to sum over all the 16. There is a good reason why it does that. But again, we won't learn that in this course. This you learn in the course in general relativity. But here you just end up with 4 terms. And they're simple, right? The g, eta or g just contributes +1 or -1, that's all. Okay? Good. Now that we've done that, now we are at the stage that we can define the Lorentz transformation. So what is the Lorentz transformation?
It's the way we switch from x to x prime.
Yeah, so basically it's a transformation from one coordinate system to another. But is there anything special about this transformation? I mean, how do you define it? So it is, you're right that it is a transformation from one coordinate system yeah, but is that enough?
No, so it has to conserve the interval.
Exactly, very good. This is the important part. That conserves the interval. This is the definition of a Lorentz transformation. Okay, Lorentz transformation is a transformation that conserves the interval. Okay, now it gets quite simple, right? So we wanted the interval to be conserved. So one example, right, is a simple translation. Right? What is a translation? Translation. Right, x mu goes to x mu prime, which is simply x mu added with some constant. Let's simply shift the origin. I can shift it in space. I can also shift it in time. Right? If there is somebody here that thinks that this is not, it gets confusing, then stop me and let me know. I'm going a little bit fast because you say that you're familiar with special relativity. I don't know if you're familiar with special relativity in this form, but this is special relativity. Yeah.
Isn't there also a coefficient? Isn't there supposed to be a coefficient with the x mu to produce the x prime? X mu prime?
This is a translation. Translation means that you're shifting the origin. This is one type. This is not the only type. Okay.
Okay.
Now, more that I note my notation. I wrote x mu prime, right? Because, for example, x2 is y. So for y prime would just be x2 prime. This is just about my notation. Now, so translation leaves the difference, right? Delta x mu is unchanged. So it's just a shift. Now there is the only other kind of linear transformation is to take the 4 vector x mu and multiply it by a matrix, right? It's a space-time independent 4x4 matrix, which I'm going to write down with one upper and one lower index. So the other kind, the only other kind of linear transformation is to multiply the 4 vector x mu by a space-time independent four by four matrix, which I'm simply going to write it down as x mu prime equal lambda mu prime nu x nu. Now again, it's not going to be that crucial in this course, but get used to it. It's not one above the other. There is a space here, right? There is like a slot. There are slots. You put the first one mu prime, second and nu. This is not the same as this. This does not exist. It is meaningless if you try to put the indices one above the other.
Sorry, is the prime over x or over mu? Like, is the index mu prime in the vector x, or is the vector x prime in the index mu?
It's actually the x mu prime. So as I wrote here, think of x2 is y, x2 is y, so y prime is x2 parenthesis prime.
So it's
So what-
x2 prime.
Yeah.
And
Okay,
that,
practically it doesn't matter, but yes.
okay.
The
Okay.
most important thing for me, from my side, pay careful attention on where you put the indices.
I'm sorry, so what's the meaning of the mu prime in lambda? Is it just lambda mu without a
That's what-
prime?
That's why I asked.
No, okay, no, I see.
I mean, it's not, the index
No,
is
it will
mu,
be-
not mu prime, right?
yeah.
Prime is,
Yeah, it will be a new prime. It will be new prime. Okay, now I see your point. No, you have to write this x. The prime would be on the mu here. You have to have it. Otherwise, it just doesn't make sense.
so the name of
there
the
is a
index
subtle-
is mu prime?
Yeah, the index will be mu prime. That's right. Because the prime is only on that index. It's not on the.
But on the left-hand side, it's the vector that's prime, not the index. Something isn't consistent.
No. I see your point. This is a 4 vector x mu. This is a 4 vector.
Mhm.
This is not a 4 vector lambda. Lambda is a matrix, right? That connects 2 frames. So the notation here is indeed. You're right. You got to a subtle point. So the notation here would be different. I'll have to write down the prime on the mu because it will connect to from the x mu to the x mu primes. So here I'll have a nu without the prime, and here I have to have the mu with the prime. So it's not the same writing the matrix as writing the vector.
It's the same index, right? If I plug in mu prime equals 1 on the left-hand side, I need to use mu
Yeah, you're right.
on
It's
the
the
left-hand side.
same index. You're right. It's the same index.
So why get a different name? That's just totally confusing. And
No, because lambda and x are not the same entities.
I understand lambda and x are not the same, but mu prime and mu are the same, right?
Yes. Let's make a simple example, and then you see exactly, right? So if I write down, for example, this equation, what is really written here, since there is a summation over nu, right? What is really written here is x mu prime is just lambda mu prime 0 x 0 plus lambda mu prime 1 x 1 plus lambda mu prime 2 x 2 plus lambda plus, I've run out of space, plus lambda mu prime 3 x 3. Right, that's what's really written here.
Okay, my question remains though, or my confusion remains. Right?
Yeah, I understand. I understand the confusion. My answer, the best answer I can give you is that the way I write down the x is a 4 vector, so I write it in one way, and lambda is a matrix. So
No, but the problem is not, well, okay, sorry, perhaps we can do that after the lecture for the sake of.
If you want, because I don't think there is a real problem here. Essentially, you'll see that this will not be your problem. Trust me on that. You'll have other problems, but not this one. Okay. Okay, so we said, so this is just a notation right now. What we said is that physically what we require from a transformation to be a Lorentz transformation is that it needs to conserve the interval. So if I go to the interval, so delta S prime, right? But what is delta S prime? I wrote it above, right? Delta S prime. Well, let's make it square so it will be easy. So this is as measured in the frame, the prime frame. So delta S prime squared, right, is just eta mu prime delta x mu prime delta x nu prime. Now I'm making a transformation. So I have this transformation law, which is right here. So let's write it down. So it's just eta mu prime, mu prime. And here I have a lambda mu prime, let's call it rho. It's what's called a dummy index, so I don't care. Delta x rho. When I say I don't care, it means I could replace rho with an alpha or beta or anything else. Since I'm summing over it anyway, then it's the same. And then I have lambda mu prime sigma delta x sigma. This, of course, needs to be equal to eta rho sigma delta x rho delta x sigma, which is just the interval as measured in the O frame. So these indices, this one, oh, what did I do? Let me go back. Yeah. This interval and this interval, or these are dummy intervals, right? Because we really have a summation here over rho and sigma. So this requirement essentially, now another thing is that I have here, I put all the indices, which means that I'm looking at element by element, right? This summation means that I'm going element by element and doing the matrix times vector multiplications element by element, right? So this will be true so long as we have that eta rho sigma is equal to lambda mu prime rho lambda mu prime sigma eta mu prime mu prime. So this is the condition for a transformation to be a legitimate Lorentz transformation. Every transformation whose elements, so every matrix basically, 4 by 4 matrix, right? A linear matrix whose elements fulfill this equation is a legitimate Lorentz transformation. Now a quick question. How many equations are there here? How many equations did I just write?
16.
16 equations, right? You see that? Because rho and sigma go 0, 1, 2, 3, each one. Now, in the right-hand side of each equation, how many terms are there?
How much is 16 squared? 256. No.
Yeah.
Yes.
There are also six,
Well,
no?
There are 16 terms, a total 256. There
No.
are 16 terms, right? Because there are
In
16.
each line there are 16 terms, and there are 16 lines.
Exactly. In each line, there are 16 terms, right?
Yes.
Because there is a summation of mu prime and u prime, which goes over 0 to 3. Okay. So the set of, so this is a Lorentz transformation. You never thought of it, right? Nobody told you. Or somebody did, I don't know. Did you see that? No, now I become less happy somehow. Okay, so the set of all these transformations, they form a group. Of course, under matrix multiplication, this is known as the Lorentz group. There is a close analogy between that and the O3, the rotational group, which is actually quite important in particle physics, but I may go through that, but not right now. Okay, so Lorentz transformations fall into several categories, right? So the first one is a simple rotation, right? So categories. So we have a rotation, right? So if we have a rotation in the XY plane, I'm going to write it down simply as lambda mu prime nu. It looks something like that. 1, 0, 0, 0, 0, 0, 0. That's going to be a cosine theta, sine theta, minus sine theta, cosine theta, 0, 0, 0, 0, 1. Right, of course, theta is the rotation angle. That's rotation in the xy plane. Right, you know that. Now, you can simply check, right? Let's do a checking, right? So if I take, so of course we have to do 16 equations. I'm not going to do 16 equations now, but let's choose one, right? So if we choose, like, let's say rho equal to 1, sigma equal to 1, right? So what is eta 1, 1 or G 1, 1? What is G 1, 1?
Last one.
What?
It's minus 1. 1, 1 is minus 1.
Minus 1, right? That's a minus 1. So now we have a summation of the matrix times eta, right? But the eta, right, mostly is going to give us zeros, right? It's going to be just when mu is equal to nu, it's going to give us something which is not 0, right? So I can write it down as this is eta 1, 1, right? So it's lambda mu prime 1, lambda nu prime 1, eta mu prime nu prime. Right, but the only thing now, and the lambda is going to give us something which is not 0 only when mu prime and nu prime are going to be either 1 or 2, because otherwise, if it's 0 and 3, we're going to get 0 from this matrix here. Right, so we're going to get lambda 1, 1, lambda 1, 1, eta 1, 1, plus lambda 2, 1, lambda 2, 1, eta 2, 2. Right, and then everything else is going to be 0. Right, you see that? You with me? But what is lambda 1, 1 times lambda 1, 1?
Cosine squared.
Yeah, and we said the eta. What is the eta 1, 1?
We just had that minus 1, right?
Minus 1. Yeah. So what we get here from this term? Minus cosine squared theta. What about this one? What is lambda 2, 1, lambda 2, 1?
Minus sine squared, and then we get a plus sign from the eta.
Yeah, exactly. Minus sine squared theta.
Times minus 1. No?
No, no.
No, because it's the same element. It's not one of them, it's both of them.
Oh, sorry, it's 1, it's 2,
Minus,
1, 2,
minus
1.
squared, minus squared, and then you have another minus 1. Right? Okay. Now you have to go over the 16 equations, right? I didn't go over the 16. So you have a total of 16 choices. What are the 16? These are choices of rho and sigma. I just gave you one example, right? Rho equal 1, sigma equal 1. Go and check, right? Of course, this is the same as rotation in 3D space, which, as we know, conserves the distance. So there is an analogy between the interval and the distance.
Can you do a more complex rotation that involves also the time component?
Yeah, it's a cool idea.
Like putting the cosine and sine in the upper left corner?
Right, yeah, exactly. So actually the only other one that we have Well, there is composite, but there's no point in doing that. It's just annoying. But yeah, what if we do rotation? Rotation in between space and time directions, right? So when time is one of the directions, right? Rotation between space and time. Well, this have a name. The technical name for that, maybe you know. Well, what is the name, if you know?
Lorentz boost.
Sorry?
What's called boost or Lorentz
Yeah,
boost?
very good. Yeah, very good. Exactly. Oh, you do know that. Maybe I'm just wasting your time. Do you want me to skip
I
it?
think only 1 or 2 people know that.
No, I have to say, I think, yeah, I'm probably
No,
not that.
do you want me to skip that part? I don't know. If you know it, then it's a waste of time for all of you. It's a pity. Somehow I have a feeling that you're not that fond of.
I don't know it.
Okay. Guys, there's nothing bad in not knowing something. And then we teach you and you know it. This is called boosts. Of course, there is a slight difference because the time goes with the opposite sign for the space. So we cannot just put a cosine and sine. Instead, we're doing two things. We're replacing the cosine and sine with the hyperbolicus cosine and hyperbolicus sine. And we add an extra minus. So the matrix of the boost matrix in the tx direction, so it looks like that. So lambda mu prime nu is cosine hyperbolicus of phi, and then minus sine hyperbolicus of phi, and then a 0, 0, and then minus sine hyperbolicus of phi, and then cosine hyperbolicus of phi, and then a 0, 0, and the rest is just 0, 0, 1, 0, 0, 0, 0, 1. So the format looks very much the same as the rotation, just because we had the extra minus sign. We had to replace the cosine with cosine hyperbolicus, and the sine with the sine hyperbolicus, and we had to have the extra minus sign. The parameter phi in particle physics has a name. It's called the rapidity. And as opposed to the angle theta, of course, changes from 0 to 2 pi. Phi can go between minus infinity to plus infinity. So it's defined over the entire space. Again, we can do a direct substitution. Again, if I take rho equal to 1, sigma equal to 1, then we end up that minus 1 is just eta 1, 1. Like lambda mu plus mu prime 1, lambda mu prime 1, eta mu prime. Again, the only non-zero terms that come with the lambda matrix, right? It's just the 0 and the 1, right? And they have to be the same because otherwise the eta matrix will give us a 0. Right? So lambda 0, 1, lambda 0, 1, eta 0, 0, plus lambda 1, 1, lambda 1, 1, eta 1, 1. What is the first term?
Minus hyperbolic sine squared.
Second term? Actually, it's a plus. Why minus? We have the eta 0, 0 is a plus.
Right, plus.
Yeah,
and there's a minus cosine squared, which is minus 1.
What is sine hyperbolical square of something minus the cosine hyperbolical square of something?
It's minus 1.
The minus 1. Check.
Yay.
So at home, you can go on and proceed with the other 15 equations if you want. You should. Until you make sure that you get the idea. Of course, what people do today is put it in a computer, but you understand why. Okay, other things which we will discuss is time reversal and space reversal. We're not going to do it here. Any general transformation can be made by taking multiplying Lorentz transformations. Again, there is no point in doing it right now. Lorentz transformations do not commute. So they're called non-abelian. I don't know if you've seen that. Are you familiar with abelian group, non-abelian groups? No. Okay, I'll see down the line if you actually need that or not. The entire set of,
They don't
what?
commute with themselves or between
No,
themselves and the rotations.
well, rotation is a Lorentz transformation. I'm only among themselves. I mean, I said that rotation is a completely legitimate Lorentz transformation. Now I'm talking of the Lorentz transformations as a set, right?
Okay.
It's a non-commutative set, so it's called a non-abelian group. Right? Rotation is a Lorentz transformation. I don't know if you ever thought of that like that, but rotation is a Lorentz transformation. Okay, the set of all these groups together with the transformations is called a Poincare group. And again, I don't think we'll go that deep in this course into that. Okay, now we can take that Lorentz transformation and put it in a somewhat more familiar form by multiplying that with the 4 vector x nu. So if I take this equation, multiply it with the 4 vector x nu, right? X nu here, right? Will be ct x y z, right? Then I can write it down. Now I'm simply using matrix times vectors multiplication. So I have a lambda mu prime nu x nu, which is of course x mu prime. So the 0 component is just ct prime equals ct cosine hyperbolicus of phi minus x sinus hyperbolicus of phi. And then x prime is just minus ct sine hyperbolicus of phi plus x times cosine hyperbolicus of phi. So the velocity at the point for which x prime is equal to 0, so if we set x prime equal to 0 here, then I can define the velocity, which is to 0, beta is just v over c, and just x over ct is just sine hyperbolicus of phi divided by cosine hyperbolicus of phi, just tangent hyperbolicus of phi. So the definition of the normalized velocity. Now I can simply use a few algebraic identities. So 1 minus tangent hyperbolicus of phi squared is just cosine hyperbolicus of phi squared minus 1. And then we already had sine hyperbolicus of phi squared is just cosine hyperbolicus of phi squared minus 1. So and from this one here, we have cosine hyperbolicus of phi is just 1 minus tangent hyperbolicus of phi squared minus 1/2, which is 1 minus beta squared minus 1/2, which I call this gamma. This is definition, right? And from here we have that sinus hyperbolicus squared, sinus hyperbolicus of phi is just did I do wrong? Oh, no, that's fine. Cosine hyperbolicus squared is just gamma, so it's just gamma squared minus 1 to the power 1/2. Which is simply gamma beta. Right? So when we end up writing CT prime equals CT times gamma, or maybe it should be the gamma in front, gamma CT minus beta x. And x prime is just gamma times x minus beta CT. And this I'm sure you've seen. Not sure if you've seen this rapidity and this form. And also I can simply use that gamma and beta to write down this matrix, the Lorentz transformation matrix, Lorentz boost, right? It's simply gamma lambda u prime nu, right? What's written here? Cosine hyperbolicus is just gamma and sine hyperbolicus is just gamma beta. So this is just gamma minus gamma beta 0, 0, and then minus gamma beta gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Ta-da! I wasn't cheating. Okay, so apparently it is whatever looks like a very abstract notation, which is it abstract. You get back the same Lorentz transformation that you're familiar with from a course in special relativity in first year. Only now that we know how to work with 4 vectors, and you get some feeling of this new notation. Yeah? You all with me?
This will be in the homework, right?
What?
This will be in the homework, right?
Of course it will be. Well, I haven't written your homework, but I've got some good feeling of what's going to be there. About the homework, it might be in the exam.
It feels like I personally think I'll need some using it in order to understand it better.
Oh, yeah. Oh, yeah. It's not that difficult. It's just, it's not difficult at all. Well, easy to say after you've been doing that for 10 years. You just need to get familiar with the notation and the work, and then you see it's pretty much straightforward. Things get very easy when you do it. Just like, it's much more natural. And you see where everything comes from. It's like, you see the mathematical structure behind it. You see that it's not It doesn't just come out of the blue. There is a very, you can see the entire mathematical structure, right? So where it comes from. Everything. I tell you, these are the things I really like about physics in general. There is a very strong mathematical basis to it. Okay, okay, a few more things. We still have some time. A few more things which are important because we will use them. So this is about Lorentz transformations. Now let's speak about scalar product and Lorentz scalars. So this is a part that I am teaching in the GR course in general relativity, and I'm not going to teach you here because it takes us away from what we actually need to learn. So there is, I told you, there are some mathematical structures that I'm not teaching, but they're still there, believe me or not. So I can use this matrix, the metric matrix, to lower indices. So I can write down I can define a covariant vector B mu as G mu nu B mu. This is really the definition. Right? So here I have this called a covariant vector. If you look very closely at this vector B mu, it's also a full vector. However, you see that the spatial components, but only the spatial components of this covariant vector, this is a covariant vector. This is a regular vector. The correct terminology for that is called a contravariant vector. Or simply vector. When we say vector, we mean a contravariant vector. That is the standard. So you don't need to use the term contravariant. Simply use vector, and that's good enough. For a vector with lower indices, then we have to use the term covariant vector, so we know it's not a regular vector. Okay, so for a covariant vector, the spatial components have the opposite sign because this G, remember, it's a +1 minus minus 1, so the spatial terms have the minus sign as those of the regular vector, but the time component has the same sign. Okay. The same sign as regular vector. And the space component, opposite sign. Spatial component, so the opposite sign. Okay. Told you it's not the same. Now I can define the scalar product between two 4 vectors. That's the definition. The scalar product between two 4 vectors A dot B is defined by A mu, B mu with a lower index. So I actually have to use the G mu nu matrix. So I can write it down as A mu, G mu nu, B mu. I cannot define the scalar product without the G mu nu. So in terms of components, this will give me A0, B0 minus A1, B1 minus A2, B2 minus A3, B2. Right now, because of symmetry, right, G mu nu is symmetric, so the order doesn't matter here. Right? Everything is symmetric, it's simple, it's nice. So A mu B mu is equal to A mu B mu because of symmetry.
This might be a stupid detail, but you mentioned the importance of upper and lower indices. So when you write out the sum as A0, B0, and so on, do you on purpose put both indices on the top, or?
Yeah. This is just a component, right? A0. This is a zero component of A.
So when
This
it's a
is
specific component, you don't care, but when it's the actual index, then it's important.
Exactly. This is a specific component. This is the zeroth component of A. A0, right, is CT. It's a time component of A.
Okay, thanks.
Besides, I tend to be more, again, this is something which I find annoying. I tend to be much more strict when I write it than what you find in normal particle physics textbooks. Because again, in particle physics, this may not be so crucial. In general relativity, this is absolutely crucial. Stupid mistakes. But yeah, so in particle physics textbooks, you always find, I often find sometimes, you know, this loosely defined some notations, which I find annoying. Okay, that's the way it is. When you read the textbooks, which I assume you all made your homework and read about the chapter 1 of Griffith. Now, this is a product of two vectors. This is invariant under Laurence transformation, which means that it is the same in all frames, in all inertial frames. So the result, this is a scalar, the resulting scalar product is invariant under Lorentz transformation. So it always gets the same result in every frame. Any two observers will agree. So it means it's identical in all inertial frames. So we say, again, the technical term is that it is a Lorentz scalar. Now, one specific example is the norm of a vector, right? So if we take A and B to be the same vector, then the norm of a 4 vector is scalar. Simply A dot A is a Lorentz scalar. Now, one last thing, which since we are running over time, and I did not, okay, I was too optimistic thinking that we could finish special relativity today. It's not good. You need to digest it a little bit, even if you've seen that. As opposed to, so a squared, the norm is A dot A, of course, it's just A mu. You know, the norm of a vector in Euclidean space that you're familiar with is always going to be positive. But in relativity, the norm of a vector does not have to be positive. And it can be also negative, right? That depends because we have this minus sign here. Now, I hope I am not, this could be, yeah, I know, this could be something that I'm confused by. Okay, so let's hope that I'm not gonna lie to you. So when we look at the vector, the norm of a vector, then A squared, it can be either greater than 0 it can be equal to 0 and it will be smaller than 0. If it is greater than 0, that means that the time component is larger than the space component. Then we call it a time-like. If it's equal to 0, then we call it a like-like or null. And if it's smaller than 0, we call it a space-like. Now, the vectors that we are familiar from the real world, right, are always time-like. I haven't defined yet to you what is my world line. I'll define it to you on next Tuesday. It's always world-like, time-like. But photons, for example, right, it's always light-like. They're null, right? They always travel at the speed of light. But there are these things which are called virtual particles, which we will discuss them next week, I hope, when we start, maybe next week or shortly afterwards, when we start discussing Feynman diagrams and virtual particles, and they are space-like. All right. So when we will describe interactions between particles, you'll see that we're going to make use of these space-like photons quite often, actually, not just photons. It's called virtual particle, which will describe exactly what it means down the line. All right, I'm past over time. Any questions?
Thank you very much.
Was this new to you, or were you familiar with all of that?
Well, I think it was new to me.
Okay, good. Okay, I saw that, you know, in other places where they teach it, they don't go as deep, and I think that they simply assume that people know that. I did not assume that you know that, because my experience tells me that students in the first year of studying special relativity do not see that, definitely not in that way. And again, I told you this is, you need to understand this notation because we're going to make a lot of use of it. I don't know if you studied, those of you who said a few of you have studied quantum field theory. I'm not sure how you could, what notations you use, because this is exactly the notation that is being used in quantum field theory. So I'm not sure what were you doing there exactly, but in any case, we're doing it here in the proper way. And if you have not studied quantum field theory, you will study it one day, maybe, then you'll see this, you run this into this over and over. Okay, no homework for today because I want to finish this part. So you've got a free week, but next week you will get a problem set and you will also try to make a tutorial. If there is something which you want me to review or to go over, please do so. I mean, last lecture was an introductory. I didn't expect you to have too many questions. This one, we're starting to do something more technical. I'm still going to keep it easy, don't worry, with some technical parts and there's some easy parts. I would imagine, and you said that not everything is fully familiar, so please review that. And if something is not familiar, then make sure that you understand it, or come to ask me, or read in the textbooks, or whatever you want. Just make sure that you understand it. All right, guys.
Once again, thank you. Goodbye.
Yes, and see you next Tuesday.
Thank you.
Bye-bye.
Thank you. Bye.
Asaf, can I still try once more about the indices?
About what?
About the indices part. אנחנו יכולים לדבר
The
בעברית?
indices, yes.
לי יותר נוח. ואני רואה
עברית, כן. אני רואה
לי
שכולם
יותר
פה
נוח.
בעברית, כן.
זהו. אני עדיין לא השתכנעתי שעניין האינדקסים תקין ומסודר. כי אתה אמרת שלמדה...
לא, האינדקסים תקינים, אני חושב
לא,
שיש פה איזושהי
ברור
נקודה
לי
מאוד...
שככה כותבים. ההסבר על למה ככה כותבים עדיין לא ריצה אותי, כי אתה התעקשת שיש הבדל בין X ללמדה, ואני מסכים, אבל אני לא מבין איך הסימונים השונים שלך עבור X מסתדרים.
השאלה איפה אתה שם את האינדקס. לא, השאלה היחידה היא, אני כנראה נכנסתי פה לאיזושהי פינה שלא הייתי צריך להיכנס אליה. השאלה, איך אתה כותב את זה? אתה יכול לכתוב X mu פריים.
אני לא רואה את המסך.
אתה לא רואה. טוב, רגע, אז אני אחזיר את השיירינג. אוקיי. איך אני אעשה את זה פה? כן. רואים עכשיו?
כן, עכשיו כן.
תראה, שאני רושם, אוקיי, יש לנו שתי מערכות ייחוס, כן? יש אחת שנקרא לה O ואחת שנקרא לה O פריים.
כן.
עכשיו אני רוצה לתאר קואורדינטה במערכת הפריימית, כן? עכשיו, במערכת הפריימית, אני אקרא לה X פריים, Y פריים, Z פריים, T פריים. נכון, C הוא קבוע.
נכון.
עכשיו אני רוצה לעשות את זה בקיצור. עכשיו, בקיצור, כשהיה לי X, Y, Z ו-T, אני פשוט קראתי לזה X מיו. שמיו זה היה אינדקס שרץ מ-0 עד 3. כלומר, X0, הכוונה היא ל-CT, X1, הכוונה היא פשוט ל-X, וכן הלאה. עכשיו, השאלה פה, אוקיי, אז איך אני קורא למערכת שאני קורא לה עם פריימים, כן? אז יש פה בעצם שתי אפשרויות שהן קצת סאבטרטיב. זה ברור שצריך לזכות X מיו פריים, יכול להיות גם X פריים מיו, נכון? או X פריים מיו. אבל יש פה איזשהו סאבטלטי, איך לקרוא לזה. עכשיו, אני משתמש במינוח X מיו פריים, כי אני אומר, אוקיי, X מיו, אם מיו נניח שווה ל-2, אז זה Y. אז בעצם הכוונה פה היא Y פריים. כן, כי אני הגדרתי לך ש-X2 שווה ל-Y. פשוט כי אני הגדרתי את זה. לכן אני לא משתמש בסוג הזה של נוטציה.
כשאתה כותב ככה, אתה בעצם שם סוגריים על X מיו ומוסיף על זה פריים, נכון?
נכון.
עכשיו, אני לא מבין איך אתה יכול להוציא את מיו פריים החוצה. כי הפריים...
מיו פריים זה בסך הכל אינדקס, נכון? מיו פריים זה אינדקס.
לא, זה מה שאני אומר, שכשאתה כותב X מיו פריים, אין לך שום דבר עם האינדקס מיו פריים. יש לך X עם האינדקס מיו, ועל זה אתה שם פריים. זו בעצם השאלה, האם הפריים הוא על X מיו או רק על מיו?
אז לא, אז הפריים הוא על כל ה-X מיו בעצם, שאני כותב את זה ככה. הפריים הוא על כל ה-X מיו, אבל אתה עלית, או אתה או מישהו אחר, עלה פה על באמת איזושהי נקודה מאוד מאוד עדינה בסימונים, כן, כי אני רשמתי X מיו פריים, והכוונה הייתה X מיו פריים, להבדיל מ-X פריים מיו, יכולתי לרשום את זה ככה, יכול להיות שאפילו בכמה טקסטבוק, בטוח שהייתי סטודנט, אני בלבלתי את הדברים האלה, אני יכול להיות שבטקסטבוק זה גם, יש כאלה שזה מבולבל, היום אני חושב שכבר לא. ולעומת זאת, כשאני רשמתי את המטריצה שמייצגת את טרנספורמציית לורנץ, אני רשמתי אותה בתור למדה, מה קרה פה? למדה מיו פריים נו. ואז בעצם הפריים היה שייך למיו, אבל בעצם זו מטריצה שמעבירה אותי ממערכת ה-O למערכת ה-O פריים. כן. אז אתה צודק שיש פה איזשהו בלבול מסוים בדיוק בנוטציה, אבל אני חושב שזה די ברור.
לא, הכוונה ברורה. השאלה הזו לא תפריע לי לענות על שיעורי הבית, אני מקווה.
לא.
אני רק מנסה להבין את המוטיבציה מאחורי זה.
זאת המוטיבציה, זאת כל המוטיבציה. המוטיבציה מסתתרת כאן, בקטע הזה, כן? שאני רושם פה את x2 שווה ל-y, אז אני רוצה להגיד y פריים, אז אני ארשום x2 פריים, ולא x פריים 2.
כי מה שהיה לי בראש זה בדיוק הפוך, מכיוון שאתה מתייחס גם מה שלי נראה הגיוני זה להתייחס לזה ההפך, כלומר, יש לנו את x שהוא איזשהו וקטור 4-ממדי אבסטרקטי, ואתה יכול להפיל אותו על תת מרחב אחד עם האינדקסים מיו, 0, 1, 2, 3, ועל מערכת צלעים אחרת עם מיו פריים.
אז זהו, זה
זה לא
יותר
נכון.
מבלבל. אז זה יותר מבלבל, כי אני לא מתייחס לוקטור בתור x, אני מתייחס אליו בתור x מיו. אני אתייחס לוקטור שלי,
למשל, כשכתבת A.B, התייחסת ל-A כאל אובייקט בפני עצמו.
נכון, A הוא אובייקט, נכון.
אז זה מה שאני אומר, אז למה אי אפשר להגיד
אבל,
A הוא אובייקט, יש לו אינדקס מיו או אינדקס מיו פריים? כי זה מסתדר יפה מאוד, אבל זה מנוגד למה שאתה, אבל אתה התעקשת שלא, שהאובייקט הוא דווקא X מיו. בגלל זה מה שבלבל אותי.
לא, אוקיי, אני מבין אותך. אני מניח, אתה צודק ש-A בעצם הוא איזשהו אובייקט מופשט, הוקטור הוא איזשהו אובייקט מופשט, אבל יש לו משמעות פיזיקלית רק כשאתה מתייחס למערכת הספציפית.
טוב, אני גם במהלך השיעור...
רק אז אתה יכול לעשות עליו איזושהי מדידה. אתה יכול לעשות איתו משהו. אוקיי, זה הולך טיפה יותר עמוק ממה שאני יכול להיכנס אליו בקורס הזה. אתה מוזמן להצטרף לקורס ביחסות כללית, שם אנחנו נלך יותר לעומק.
אני עברתי את הקורס במחקר המתמטיקה בגיאומטריה דיפרנציאלית, בגלל זה אני כן...
אז זה קרוב מאוד.
בגלל זה אני מתעלל, בגלל זה הסימנים האלה מציקים לי, אבל בסדר.
רגע, זה מה שמקובל, זה מה שאני ראיתי בספרות הפיזיקה. במתמטיקה אתה יכול להיות שאתה צודק ויש שם סימנים קצת אחרים, אני לא ממש קורא את הספרים של המתמטיקאים, למרות שהחומר הוא מאוד מאוד דומה. אבל כן, אני מסכים איתך שיש פה נקודה שהיא מאוד מאוד עדינה. בסדר?
בסדר, תודה רבה.
בבקשה.
עוד בשבוע הבא.
עוד שבוע הבא. אחד.